Hello, let's walk through the pretest. Number one, it's talking about this diagram here. It says two positive charges of magnitude q are each a distance d from origin A of a coordinate system as shown above. Now, which of the following points is the electric field least in magnitude? So both of the charges are positive, and we know what the electric field looks like. Remember, it's asymptotic. And the field lines always go from positive to negative. So what I know here is that the electric field has to be 0 in the middle. So least in magnitude, it would have to be at point A because it's right in the middle. Number 2 says, at which of the following points is the electric potential greatest in magnitude? We know that the electric potential is a scalar quantity, and it's just the sum of the two charges. So the place where R is the least for both of them would have to be at point A, because that is the shortest distance between the two. So that would give us the greatest potential. Number 3, two isolated charges, positive Q and negative Q, are 2 centimeters apart. If F is the magnitude of the force acting on charge negative 2Q, what are the magnitude and direction of the force acting on charge positive Q? So I have negative 2Q and positive Q. Now they're going to be attracted to each other, but they're going to have the same force. So if I say this is force on 1 by 2, and this is force on 2 by 1, F1, 2 has to equal F2, 1. So by Newton's third law, we know the force has to be the same and it has to be toward the other charge. So the correct answer is C. A positive charge of 10 to the negative 6 coulomb is placed on an insulated solid conducting sphere. Which of the following is true? We know when we have a conductor, the electric field is 0 inside. And we also know that the charge resides on the surface. Another thing that we know is if we hook up two conductors and we let them touch, they're going to share the charge because it's like having one object, so they're going to share the charge. So we know A is wrong because a charge does not reside uniformly. The electric field inside the sphere is constant in magnitude but not 0. We just said it's 0. The electric field in the region surrounding the sphere increases with increasing distance from the sphere. The opposite is true. By Coulomb's law, the electric force decreases and so does the electric field. An insulated metal object acquires a net positive charge when brought near to but not in contact with the sphere. If they were close to each other, so let's say this one has a positive charge and I bring it close to another one, what it's going to do is it's going to induce and polarize the charge on the surface of the other one, but it's not going to have a net charge. So D is wrong. So E has to be the correct answer. When a second conducting sphere is connected by a conducting wire to the first sphere, charge is transferred until the electric potentials of the two spheres are equal. So them being connected by a conducting wire means that they're connected and they're one object, so they're going to share the charge. A parallel plate capacitor is charged by connection to a battery. If the battery is disconnected and the separation between the plates is increased, what will happen to the charge on the capacitor and voltage across it? So we know that C is equal to EAD, and we also know that C is equal to Q over V. Since the battery, if the battery is disconnected and the separation between the plates is increased, what will happen to the charge on the capacitor and the voltage across it? So the battery is disconnected and we see that the separation of the plates is increased. So C is inversely proportional to D. So that means if I increase the distance, then the capacitance is going to decrease. So what will happen to the charge on the capacitor and the voltage across it? Well, so the distance increases, the capacitance decreases. So that means that the charge that it can hold per potential difference has to decrease. But we also know that V equals ED. And if the distance increases, that means the voltage decreases. And Q is equal to CV. So if the capacitance decreases and the voltage decreases, then that must mean that Q also decreases. So the correct answer is both decrease. A wire of length L and radius R has a resistance R. What is the resistance of a second wire made from the same material that has a length L over 2 and radius R over 2? Well, the resistance R is the resistivity, which depends on the material, and so that one's not going to change because they're the same, and the length over the area. The area of a wire is pi r squared. So if I half the radius, that means the area is going to change, is going to be a quarter as big. So the area is a quarter as big. So R is equal to, or proportional to 1/2 L divided by 1/4 A. The 4 goes up here, the 2 comes down, and so the resistance is going to be twice as much. Which of the two arrangements of resistors shown above have the same resistance between the terminals? So all we have to do is calculate it out here. When they're in series, I know I can just add them up. When they're parallel, it's the inverse, or the reciprocals that we add. So we can see that this one is 2 ohms, 2 plus 2 is 4 ohms, and this is 1/2 plus 1/2, which is 1, and then if I take the reciprocal of that, it's still 1, so this is 1 ohm, and then 1/4 plus 1/4 is equal to 2 over 4. Take the reciprocal of that, and I have 2, so this is 2 ohms. And we can see that it's 1 and 4 that have the same resistance. A lamp, a voltmeter V, an ammeter A, and a battery with 0 internal resistance are connected as shown above. Connecting another lamp in parallel with the first lamp as shown by the dashed lines would. So what it's asking us here is what's going to happen to the current going through here. So the lamp, we can think of it as having its power that radiates out as light is IV. We know when we connect it, the current is going to split. So let's say that they both have the same resistance. If I had a total current I coming over here, this one's going to have half of it, and this one's also going to get half of it. But the voltage across each, remember that the voltage across parallel components is the same. So the power or the light radiating is going to be less because there's less current, but the voltage stays the same. So we want to see what's going to happen. Well, first one says increase in the ammeter reading. Well, once the current splits up, it's going to reunite here. And so we're going to get the total current going through the ammeter. So there is no change in it. And we know that the total current in has to be the total current coming out by Kirchhoff's second law. So there's no change in the ammeter, so it can't be B either. And then the voltmeter is just measuring the voltage across. Now the voltage across here has to be the same across the lamp, and because the second lamp is parallel, it's also the same, so the voltmeter doesn't change either. So E is the correct answer. Number 9, 9 and 10 relate to the 5 incomplete circuits below composed of resistors R, all of equal resistance, and capacitor C, all of equal capacitance. A battery that can be used to complete any of the circuits is available. Into which circuit should the battery be connected to obtain the greatest steady power dissipation? So in this case, it's asking us where, if we connect the battery, are we going to get the most resistance? Because the most resistance is going to give us the greatest power dissipation. We can see this by P equals IV, but Ohm's law tells us that V equals IR. So in place of V, I can substitute and I get I squared times R. So we want to find the one that has the most current or the most resistance. I can also substitute in here to get something in terms of V and R. So I is equal to V over R. So if I plug it in here, I also get V squared over R squared times R, which is just V squared over R. So we can find any of these relationships to find where the greatest steady power dissipation would occur. So this equivalent resistance for part A is just going to be 2R. So that one will give us 2R. What's going to happen here is the current is going to flow and then get stuck at the capacitor. So none of it's going to flow to the resistor. So this is going to have 0 power dissipation. In this case here, what's going to happen is after a long time, no current is going to flow here. It's going to get stuck, and so it's just going to follow between the two resistors. So again, we have equivalent resistance is just 2R. On the second one, we have resistors that are in parallel. So the resistors in parallel are going to give us, so 1 over R equivalent is 1 over R plus 1 over R. And so that's just 2 over R. So that means that the equivalent resistance is R over 2. So that one's going to have less resistance than either A or C. The next one is going to give us current, and after a while it's not going to go through the capacitor, and it's just going to go through the two parallel resistors, which we already figured out is just 1/2 R. And then it's going to add to the second R, which is just R, and so we'll get 3/2 R. So now we have to choose between the two that have the equivalent resistance. So we have to make an assumption here that it's not talking about after a long time, but rather throughout time, starting from the beginning. So if we look at C, we know that some of the current is going to be thrown into the capacitor until it gets filled. So the correct answer has to be A, because that one doesn't have a capacitor, so it doesn't diverge the current. For number 10, it says, which circuit will retain stored energy if the battery is connected to it and then disconnected? Well, we have to see which one would not have the current, it doesn't make a closed loop with the capacitor such that it could dissipate the energy. Well, A doesn't have a capacitor, so it can't be A. B charges it all up, and then if we disconnect the battery, the charge just stays in the capacitor. Part C would make a closed loop. So it would run and run until all the energy was dissipated across resistors. D doesn't have a resistor, so a capacitor, so it can't store any energy. And then right in here, this one has 2 loops if it was disconnected, and so it would dissipate the energy, so it can't be E. So the correct answer has to be B. So here is a first free response. We have to find the magnitude and direction of the electric field at point P. Remember that we assume that there is a positive test charge at point P. So if I call this one 1, this one 2, and this one 3, if I see the electric field due to charge 1, I know it's going to be pointing to the right, because if I had put a positive test charge here, it would repel it. So this would be E1. But if I look at 2, it would also repel it, so it would push it down. And so the electric field due to charge 2 would be downwards. And then lastly, the charge 3 would attract a positive charge at point P, so it would also point to the positive x direction to the right. So by looking at this picture, I know that the x component of the net electric field has to be due to E3 plus E1. I know that EY is due to E2, and it's in the negative y direction. And so using Pythagorean theorem and the things that I know about vectors, I know that E has to equal to EX squared plus EY squared. And theta has to equal to the inverse tangent of EY over EX. So let's go ahead and do a few more calculations. We need to know what the distance is from the first charge to point P, and this is an equilateral triangle, so I can assume that P is halfway between charge 1 and charge 3. So if the total distance is 1.25, then halfway is 0.625 meters. Now, looking at the distance from charge 2 to point P after you use Pythagorean theorem, I'm looking for one of the sides. So what I would be looking for is the hypotenuse, which is 1.25 squared minus the other length, which is 0.625 squared. And when I put that into the calculator, I get 1.08 meters for that length. So what I'm looking at is this triangle right here. And that's a right triangle. The hypotenuse is 1.25, one of the legs is 0.625, and by Pythagorean's theorem I know that the other leg is 1.08 meters. So now all I have to do is find out my EX's. So EX is equal to KQ1 over R1 squared plus KQ2 over R2 squared, which is 9 times 10 to the 9. Then I have Q1 is positive 2.75 times 10 to the negative 6 divided by the distance, which is 0.625 squared plus 9 times 10 to the 9 times 1.72 times 10 to the negative 6 divided by 0.625 squared. When I do that, I get an answer for my EX. And the answer that I get is 102.989 newtons per coulomb. Now I have to find my EY, and that is just E3, which is KQ3 over R3 squared, 9 times 10 to the 9, and then times 1.7 7.45 times 10 to the negative 6 divided by 1.08 squared, which gives me 57870 newtons per coulomb. So now to find E, I just take the square root of both of these and the sum of the squares, and that would give me square root of 102,989 squared plus 57,870 squared, which gives me 134 newtons per coulomb. Theta is the inverse tangent, but EY is in the negative direction, so I have to use the negative sign here, and that's 57,870 divided by the positive 102,989, and that gives me negative 29 degrees. But it has to be between 0 and 360. So my true theta is 360 minus 29, which is 331 degrees. So finally I have that E is equal to 118,134 newtons per coulomb at 331 degrees. The next part asks me to find the electric potential. The electric potential is a scalar, so all I have to do is sum them up. So V at point P is just KQ1 over R1 plus KQ2 over R2 plus KQ3 over R3. So what I can do is I can take out the K, since it's common to all of them, factor it out, and then Q1 is 2.75 times 10 to the negative 6 divided by 0.625. Need a little bit more room. Okay, it's not gonna let me. Plus Q2, which is negative 1.72 times 10 to the negative 6 divided by 0.625, plus Q3, which is 7.45 times 10 to the negative 6. Divided by the distance, which for that one is 1.08. Plugging this into my calculator, I get 76,915 volts. So to find the electric potential, all we have to do is take the potential due to each one of those charges, and because it's scalar, the sign does matter, so we subtract the negative one, and then we get the answer of 76,915. For the next part, it says if a charge Q4 of positive 2 microcoulombs is brought from infinity to point P, what is the potential energy of the charge at point P? All we have to do is to find U of 4, we just multiply Q4 times V at point P. So it's just 2 times 10 to the negative 6 times the potential at point P. And when we do that, we should get 0.154 joules. Find the magnitude and direction of the force on Q4 due to the other charges. Well, we know that F is equal to QE. So all we have to do is multiply Q, which is 2 times 10 to the negative 6, times 118,134. And we get 0.236 newtons at 331 degrees. And they point in the same direction because it's a positive charge. If, for example, Q4 had been negative, we would have to take that 331 and subtract 180, so they would be pointing in the opposite direction. Number 2, find the equivalent capacitance for the circuit. What's important in this is you always want to start on the outside and work your way back in. So I'll draw successive pictures of what you should see. So this picture here is going to become this next picture. So we have the 100 volts, and then we still have that 5 microfarad capacitor. But what we're going to do is we're going to combine these two parallel capacitors into one capacitor. So this is our second picture. Because capacitors in parallel are just added straight forward, capacitors in series are inverses, so the opposite of resistors. So 2 and 4 is 6, and this is 3. So now I have the two outside capacitors are in series. So my next picture is going to look like this. So this is 100 volts, this is 5, and then 1/6 plus 1/3 is equal to 3/6. If I flip it over, that means that the capacitance of these two is 2. Now I have 2 in parallel that will just become one equivalent capacitor. And since they're in parallel, that means I just add them straight forward. So it's 7. So the equivalent capacitance is just 7 microfarad. What is the potential difference across the 5 microfarad capacitor? Well, the 5 microfarad capacitor is parallel to the 100 volts. And so the potential difference is just 100 volts. Let's look at resistors. We're going to do the same thing here. We're going to draw equivalent pictures. So I'm going to look at the outside and work my way in. So my next picture would look like this. So here's my resistor. Here's my other resistor. And then this picture. So here's 20, here's 40, here's 12, here's 8. But what I've added are the two 40s. They're in parallel. So remember that R in series is R1 plus R2. R in parallel, you're adding the inverses. So if I add those two together, I get 140 plus 140, which is 2/40. If I flip it, I get that these two are just 20. So now I look at the outside, and I'm going to draw another equivalent circuit. And what I'm adding are the 3 on the outside. So I'm adding the 8, the 20, and the 12. And that becomes 8 and 20 is 28. 28 and 12 is going to be 40. So this is still my 20 ohm. This one's still my 40. But now this one is also 40. My next picture is going to look like this. So this one is 20, but I've already added two 40s before, and I know I get half, which is 20. So now those are in series, and I get my final picture. And 20 and 20 is 40. So the equivalent resistance is just 40 ohms. Let's look at our last problem. So it's important here to imagine what's going on. And if we think about the charge is going to go up, go through the 10 ohm resistor. There's going to be a voltage drop. It's going to keep going here, and then the current is going to split. But it's important to read this, it's after a long time. So charge is going to accumulate here. And once it gets full, just like a dam, there's not going to be any flow going that way. So it'll just come down the 6 ohm resistor, and I'll get a voltage drop. It's going to go through here, and then it's going to split these two ways. And remember that the more current is going to go through the least resistor. So the 4 ohm is going to get 3 times as much as the 12 ohm. It's going to go through here, and this is the battery. So when I'm talking about the terminal voltage, I mean the voltage across here. So there's another voltage drop across the 1 ohm, and that's what I'm going to try to measure for part A. So it's the terminal voltage. So what I have to do is I have to find the equivalent resistance. So the successive picture to this one is that I'm going to have the battery, the 1 ohm resistor, the 10 ohm resistor, 6 ohm resistor, and then the equivalent resistance for the one on the bottom. So here's 80 volts, 1 ohms, 10, this one's 6. This bottom one here is just 1 over 12 plus 1 over 4, which is just 4 12s. And if I flip it over, I'll get 3. So that's 3 amps. These are in series, so I can just write the equivalent resistor as a sum of 10, 6, 3, and 1, which is 20 ohms. So I need to find the total current, which is just V over R. And I have 80 over 20, so the total current is 4 amps. So that means that 4 amps are running through here. And as it goes through the resistors, there's going to be a voltage drop. So as it goes through here, the voltage drop is going to be IR, which is 4 times 10, which is 40. Then it's going to go through here, which is 6 times 4, which is 24. It's going to go through this equivalent resistance right here, which is 3. 3 times 4 is 12. And then it's going to go through the 1 amp, so that's 4 times 1, which is 4. If I add the 40 and the 24, that's 64. 64 and 12 is 76. 76 and 4 is 80. And that's just Kirchhoff's first law, that the potential drop across the loop is 0. So I start off with 80, I lose 40, I lose 24, I lose 12, I lose 4, and so I have 0 voltage left. But across the terminal is just going to be 80. So VT is just going to be the 80 volts minus the voltage drop across the internal resistor, which is just 4. So the voltage, terminal voltage is just 76 volts. For part B, it says determine the current in the 4 ohm resistor. So I know that 4 amps are going through here, 4 amps are also going through here, 4 amps are also coming out through here because they're in series. But then in here it splits up. So I know that those 4 amps, it's going to have a 3-to-1 ratio. So the only way that that can happen is the 4 ohm resistor will get 3 amps and the 12 ohm resistor will get 1. If I add those two together, I get the 4 amps, which is the total current, and that's Kirchhoff's second law. So the answer is 3 amps. Part C, determine the current, what is the charge stored on one of the capacitor plates? If I look back in the picture, I know what the voltage drop is across the 6 ohm resistor. That means that these two are parallel to each other. So the voltage drop across the 5 microfarad capacitor is also 24 volts. So it's asking me for the charge. Well, I know that C equals Q over V, and that means that Q is equal to CV, which is just 5 times 10 to the negative 6 for the microfarads times the 24 volts. When I do that, I get 120 microcoulombs. D. How long will it take for the 10 ohm resistor to consume as much energy from the circuit as is stored in the capacitor? So first we have to find the energy stored in the capacitor, which is given by U 1/2 CV squared. So that's 1/2 times 5 times 10 to the negative 6, and then the voltage is 24, and then square that, and I get 1,440 microjoules. So now I have to find the power dissipated by the 10 ohm resistor. Well, remember that power is equal to IV, or I squared times R. I know that the current going through the 10 ohm resistor is 4, and then it's a 10 ohm resistor, so that's 10. So I get 160 watts. Now I know that power is also work over time, but that's the same as the energy stored in there divided by time. So if I solve for time, I get the energy stored divided by the power dissipated. So I take my 1,440 microjoules divided by 160 watts, and I should get 9 times 10 to the negative 9 times 10 to the negative 6 seconds.